We'll finish first two things that were pending from the earlier discussion. One is the continuity equation and Pauli matrices. So, we have talked about angular momentum in very brief. We will talk about Pauli matrices and some of the properties of Pauli matrices. And then we will get ahead with a new topic called as approximate methods in quantum mechanics, which involves learning perturbation theory and corrections, sorry about that, the corrections to energy and eigenfunction. We will talk about non-degenerate perturbation theory and then degenerate perturbation theory and apply it to a few examples. And then probably go over to the time in dependent perturbation theory. This what I am talking about here is a time independent perturbation theory. Okay. So, let me do continuity equation, and it has been written earlier, but let us derive it. This is also called as charge continuity equation and so on. So, let us just assume a region in space which has no source of charge or current. So, no source of charge and current. And we will sort of derive a continuity equation. So, what we have is that the Hamiltonian is given by minus h square h cross square over 2 m and a del square plus a v of r, and this v of r could be a function of r theta and phi, but mostly it depends only on r, that is the radial variable, and is a real quantity. Okay. So, we have for the Schrodinger equation, we have h psi equal to I h d psi dt, I h cross d psi dt. Let us call this as equation 1, this as equation 2, and let us take a conjugate of this equation, equation 2. So, we have h psi star equal to minus I h cross d psi star dt. Remember that h is equal to h star because h is a Hermitian operator. So, let us call this as 3. Now, you multiply 2 by psi star and 3 by psi, and then finally subtract. And if you do that, then what happens is that, so you have a psi star h psi minus psi h psi star, which is equal to I h cross psi star d psi dt, and minus, so this will be so plus I h cross psi d psi star dt. Okay. So, now what we do is that we put it into this equation. So, we put 1 replacing h, and let us call this as 4. Okay. So, put 1 in 4, and then we have so minus, so we have this psi star and minus h square by 2 m del square plus v of r, and you have psi, and that is minus psi, we have minus h square over 2 m del square plus v of r, and we have a psi star, and then we have a I h cross d dt of, so you have a psi star d psi dt and a psi d psi star dt. So, this can be written as a d dt of psi star. Okay. And as I told that we are talking about a region where there is no source for charge or current. So, this would be psi star and minus h square over 2 m del square psi and plus V of r is a real quantity. So, V of r and a psi star psi, and we have a plus psi, and then you have a h cross square over 2 m del square psi, and then we have V of r. So, there is a minus sign here, and then that will be minus V of r psi star psi equal to I h cross. To remind you, this is called as the probability density. So, which is equal to rho. So, rho is equal to psi star psi. Okay. And this conveniently cancels out, and what we have is that we can write this term as minus h cross square over 2 m and divergence of psi star del psi minus psi del psi star, and you have a I h cross d rho dt. Okay. If you define, so one h cross goes away and this I can be brought downstairs, so that this I reappears here, and if we define j which is a function of say r and t in general, this is equal to psi star with a h cross over 2 m I and a psi star del psi minus psi del psi star. This is this gives you that divergence of j plus a del rho del t is equal to 0. Okay. So, this is the equation of continuity. And if you have a source term there, then of course, the right hand side will not be equal to 0, that is equal to the source term that is present. So, this is precisely the equation of continuity, which is expected to hold good for any system that we discuss, or we have discussed, or we are going to discuss. Okay. So, let us now go on to another topic which is called as a Pauli spin matrices. So, to remind you that spin does not arise naturally in non-relativistic quantum mechanics. Okay. So, we have to put that spinner, if a particle has a spin, the spinner wave function has to be put in by hand, which otherwise naturally occurs in the Dirac equation. Okay. So, in any case, we will put simply by hand, and then the spinner wave function has a dimension which is 2s plus 1. So, 2s plus 1 is a dimension, and any spin operators they have the dimension of 2s plus 1 into 2s plus 1. Okay. So, for s equal to half, we have a 2 component wave function, and we have an operator which is a 2 cross 2. For s equal to 1, we have a 3 component wave function, and we have a 3 cross 3 operator whose eigenvalues are going to be the eigenvalues for the spin operator, and the eigenfunctions are called as the spinner eigenfunctions. Okay. So, what are important in this context are s equal to half operators, and these operators are known as Pauli spin matrices. They are in general denoted by this sigma. So, sigma, it has 3 components, sigma x, sigma y and sigma z. Okay. And in general, a spin and this spin half operators or this Pauli matrices have this relation, thus s equal to h cross by 2. So, h cross is the scale of the angular momentum including the spin angular momentum. So, it sort of absorbs that h cross there, so that sigma can be written in terms of the just simply numbers because the dimension has already been taken into account. So, the three Pauli spin matrices are 0, 1, 1, 0, sigma y equal to, that is for sigma x, it is 0 minus I 0, okay, and the sigma z which is diagonal 1, 0, 0, minus 1. Okay. So, whichever you take, they have certain properties that are common, and one of the property that is common is that the eigenvalue of each one of them are plus minus 1. Okay. And suppose you talk about sigma z, and then the wave function corresponding to that. So, let us call it as chi up corresponding to the plus 1 eigenvalue, this has a form 1 0, whereas the chi down corresponding to the minus 1 eigenvalue, this is equal to a 0 1. And of course, there are other things such as a trace equal to 0 of each one of them. You can see that the sum of the diagonal elements equal to 0 and so on. We are just going to come to that soon, but anything a spin 1 system, for example, which are not the Pauli matrices, but these are spin 1, and these, as I said, that they will be 3 by 3. So, it is 1 by root 2 0 1 0 1 0 1 and 0 1 0, and the Sx Sy Sx I have already written down, it is 1 divided by I root 2, and then you have a 0 1 0 minus 1 0 1 0 minus 1 0, and Sz again it is diagonal 1 0 0 0 0 0 0 0 minus 1. Okay. So, in each of these cases one usually chooses Sz to be diagonal, and nevertheless, I mean, they all have these properties which are some of the properties are quite universal for all the spin matrices. Okay. It is also useful at times for some problems to combine this Sx and Sy as writing it as Sx plus Isy and S minus as Sx minus Isy, and these are called as a raising spin operator, and the other one is called as a lowering spin operator. Okay. And they are called raising because they raise the eigenvalue by 1. In any case, we just do not go too much into details. You can read and get some knowledge about these things, and in addition to that, there will be some assignment problems that will help you to get more familiar with these spin matrices. It is 1 0 0 and 0 1 0 and so on. Okay. The eigenvalues for this are chi 1 is equal to 1 0 0, chi 2 is equal to 0 1 0, and chi 3 equal to 0 0 1. Okay. So, let us repeat some properties of this Pauli matrices, and so these are really some key properties which are often used. So, this is for an arbitrary vector rather. We have this sigma dot A, we can write this down as sigma x A x plus sigma y A y plus a sigma z a z, and this can be written as a z a x minus I a y and a x plus I a y and minus a z. These are Hermitian matrices, and the way you should check hermiticity is that you interchange the row and column, which is like taking a transpose, and then you should also take the complex conjugate. Now, if you take a transpose, then this a x plus I a y goes here and this one comes down, but then when you take a transpose, this I will change sign and you will have the same matrix. So, all these are Hermitian matrices. So, what are the commutation relations? And in fact, these are important. All of these Sx, Sy, Sz that you see there, they do not commute with each other, and there is a general commutation relation that Si Sj is equal to I epsilon I j k Sk. You can put a H cross here. Okay. So, H cross equal to 1 is taken, but you should not take it all the time. If you want, you write a H cross here. So, it is a I H cross, which means that they follow a nice cyclic relation where Sx Sy commutation will give you a I Sz, I H cross Sz. If you reverse the order, that is, if you take Sy Sx, then you will get a minus I Sz. Okay? That is because the epsilon I j k, if it is not cyclic, it is called a Levi-Civita symbol. It when these I j k are clockwise or taken cyclic in a cyclic order, they give you 1. If two of the indices is equal to 0, then it is, if two of the indices are same, then it is equal to 0, and if you interchange two indices, that is I going to k, k going to 1, and then j going to I going to j, and so on. So, if you change two of them, then you again bring back a sign. So, each time you change these cyclic property of this indices I j k, you bring up a negative sign. Two of these indices become same, you have it 0, and that is what the property is. So, Sx is of course equal to 0 because I and j are same indices. Okay, so we write down the commutation relations for these sigma matrices, and the sigma matrices have the same commutation relation, sigma x, sigma y. This is equal to I sigma z, and sigma z sigma x is equal to I sigma y, and sigma y sigma z is equal to I sigma x. If you reverse any of the indices or rather take it in the other direction, that is not sigma x y, sigma x sigma y, but it's sigma y sigma x, you are bound to get a minus sign here. Okay, so these are all understood. So, sigma I sigma j, in general this is equal to I epsilon I j k sigma k, very similar to what I have spoken for any general spin matrices or any general, I mean spin operators or any general angular momentum operators. Okay. This has some special relations which are the anti-commutation relation. And these anti-commutation relations are written as the sigma x sigma y with a plus sign. This is equal to sigma y sigma z with a plus sign equal to sigma z sigma x with a plus sign. This is equal to 0. Okay, so the anti-commutation of a pair of them is always equal to 0. Now, what it means is that you have a sigma x sigma y plus a sigma y sigma x. This is equal to 0. You see that the commutation relation actually is a minus sign, sigma I sigma j minus sigma j sigma I. That is the commutation relation, that is equal to I epsilon I j k sigma k. However, these anti-commutations are written with a plus sign in between. And if you combine these commutation and anti-commutation relation, then you get something nice, because let us see for one of them. So, sigma x sigma y minus sigma y sigma x is equal to I sigma z, that is for the commutation relation, and for the anti-commutation relation we have this sigma y sigma x, this is equal to 0, and if you add both of them, then it gives you 2 sigma x sigma y, this is equal to I sigma z. So, that tells you that sigma x sigma y is equal to I over 2 sigma z. So, if you take the two matrices and multiply them in this order, of course, you have to maintain the order, because matrix multiplication the order needs to be respected. Okay, so, so you have a sigma x and sigma y, and if you multiply them in this order, you get I by 2 sigma z. So, that is an important property, and we also have the square of them is equal to 1. So, sigma x square equal to sigma y square equal to sigma z square, that is equal to 1, but 1 I should write it a little carefully, because now they are no longer just 1, but there is an identity matrix, 2 by 2 identity matrix. Okay. So, and some other properties are, so this property, just to generalize it, so it is like sigma I sigma j is equal to I by 2 sigma k, and you should keep that cyclic order of x, y and z, or I, j and k. Okay. So, let us take a simple example for these properties, the one that we just saw, the commutation, anti-commutation, and the square of them, each one of them is equal to 1. So, let us say that you are given to simplify sigma x, sigma y, sigma z, sigma y, sigma z, sigma x. Okay. So, what is the a product of all these matrices? And one way, of course, you just simply multiply them, write 2 by 2 matrices and keep multiplying, but that is not the point. I mean, here what you can do is that you have a sigma z sigma x, that is equal to this is equal to I by 2 sigma y. Okay. And then you have a sigma y here. So, this sigma y and this sigma y will give you 1, because sigma y square is equal to 1. So, till now we got sigma y sigma z, and then we have a I by 2 coming in, and the rest will be equal to 1. Now, again the sigma y sigma z will get another I by 2 here, and we will write that as sigma x square, because sigma x coming from here. So, this again becomes equal to 1. So, it becomes I square over 4, which is minus 1 over 4, and of course, minus 1 over 4 means that minus 1 over 4 into an identity matrix. Okay. So, that is the answer for this. You may want to calculate, so this is another property, suppose so theta by 2, and there is no particular reason you can write it as theta, but what I am trying to show is that how to actually calculate the exponentiation of the Pauli matrices, because this is important when you talk about rotation in spin space. So, if you are talking about s equal to half, that is spin half objects, and consider the rotations, and this is going to be the rotation operator, and this can be simplified, because you have a you can sort of expand this. So, this is I theta by 2 sigma y plus 1 by 2 factorial theta by 2 square sigma y square, and so on and so forth, 1 by 3 factorial theta by 2 whole cube sigma y cube, and so on. Now, remember that sigma y square is equal to 1, or this identity matrix, that tells you that sigma y cube or any odd power of sigma y is simply equal to sigma y. So, you have the odd powers of sigma y will give you just a sigma y, and even powers of sigma y will be free from sigma y, because it is sigma y square is equal to 1. So, this exponential I theta by 2 sigma y, so the even powers will combine to give you the expansion of cosine. So, this is like a cosine theta by 2 multiplied by this 1. This 1 is often called as sigma 0, that is the identity matrix, and plus I sigma y sine theta by 2, because the odd powers will give you a sigma y and will give you the expansion of these sine function. So, this is nothing but equal to sigma 0 cosine theta by 2 plus I sigma y sine theta by 2. Okay. So, then another property that any 2 by 2 matrix, any arbitrary 2 by 2 matrix can be written in terms of sigma 0 and the components of sigma, or let us write it as sigma I with I equal to x, y and z. Okay. And this is easy to show. Let us take a general matrix with its component as M11, M12, M21, M22, and this can be written as M11 plus M22 divided by 2 sigma 0, that is identity, and then you have a M11 minus M22 divided by 2 sigma z, and then M12 plus M21 divided by 2 sigma x plus M12 minus M21 with the I here and by 2 sigma y, and this is nothing but these A0 sigma 0 plus A dot sigma, where A's are these the coefficients of sigma x, sigma y and sigma z. So, A0 is equal to half of trace of M, and of course, we have trace of sigma I equal to 0 and sigma I square equal to 1. All right. So, these are in brief some of the properties of the Pauli matrices, which are the spin angular momentum corresponding to spin half, and these have certain relations, and these relations are important in solving problems, or they would give rise to, or rather they help us to formulate the properties of these spin half objects. So, let us go on to a new topic which is known as the perturbation theory. And in general, they form a class of solutions which are known as the approximate methods. And as the name suggests, that this is not an exact solution, but it is a solution which is approximately done, but how good that approximation is will depend upon how controlled the approximation is, and how well we can explain these situations as a limiting case, or when the this perturbation goes to 0, whether we recover the results that we have obtained for the unperturbed problem. Okay. So, in general, very few problems in real world, in quantum mechanics or otherwise, they are exactly solvable. There are very few problems, and in fact, we have encountered this in classical mechanics, where just barely 2 particle problems are, you can solve them, even though that looks difficult, because you need 6 coordinates for 2 particles, and you have only 3 momentum conservation equations, and one energy conservation equation. So, you have four these equations, but 6 unknowns. Somehow we could solve this going to the center of mass frame and establishing a relationship between the lab frame and the center of mass frame. And we have seen such solutions. Going to 3 body becomes very difficult, and most of the time it is unsolvable. However, statistical mechanics routinely takes into account Avogadro number of particles and present a statistical description which seem to work very well. Here we are not talking about that, we are simply talking about a Hamiltonian which has got 2 parts, let us say the H naught and some part which is H prime, and of course, we know that this H naught and H prime, they do not commute, and so H naught and H do not commute as well. But why these approximate method works is that when you have these H prime, the expectation value of that as compared to this H naught, that is much smaller than 1, okay? Or you can say that the expectation value of H prime and the expectation value of H naught, it is much smaller than H naught. So, there is an ambiguity that you may notice that we are talking about expectation values without knowing the eigenfunctions of these H prime, because certainly we do not know the exact solution of H. Then how do we know the how to actually take this expectation value, that is what are the eigenfunctions used for evaluating the numerator for this problem. And the answer is that we are still using the eigenfunctions of the unperturbed problem, that is those of H 0, and the reason that they work is that these perturbation does not take you far away from the unperturbed problem. If it does, then of course, this perturbation theory will not work and the approximation methods that we are talking about will not work. But it works in most of the cases where the strength of the perturbation is small. Say we talk about hydrogen atom, and then you can use an electric field or a magnetic field which is weak enough such that it does not cause the hydrogen atom to ionize, that is it does not get converted into an ion, so that the perturbation term or the energy associated with the electric field or the magnetic field, it is much smaller than the minus 13.6 electron volt, and in those cases it will work, and we will see the problems which are called a Stark effect and Zeeman effect there. Okay, so we use perturbation theory and one can actually build up a flow chart that this is a perturbation theory, and so this has semi-classical thing which is called as WKB approximation, and WKB it's Wenzel, Kremers and Brillouin. So, that is semi-classical approximation, and then one can use it in continuous systems. Which gives you scattering theory, and the scattering these scattering matrices and this partial wave approximation to get you the scattering cross section. And we are mostly interested in this part where we talk about discrete system or quantized systems with discrete energy levels, and for that we have a time independent perturbation theory, and we have a time dependent perturbation theory. Okay. So, this will call as a TIPT, time independent perturbation theory, and this will be called as a TDPT, time dependent perturbation theory. Okay. So, it is going to be a little bit of mathematics, but that is because I am deriving everything from first principles, but one shouldn't be bothered about the mathematics. The final result is usually very simple and easy to apply to systems that you want to. So, let us do this TIPT, or the time independent perturbation theory, and build up the basis. So, you have a Hamiltonian which can be written as H 0 plus H prime, but now to explain the smallness of this H prime, let me put a lambda, and so that I can actually do a perturbation theory in orders of lambda. Okay. And so, lambda is basically a term which is much smaller than 1, then we do not have to talk about the expectation values of H prime and H naught that we have talked about before. So, we have introduced by hand a parameter which is much smaller than 1, and you have to also acknowledge the fact that this problem is known, that is this is the unperturbed problem, and these 0 actually refers to the unperturbed problem or the 0th order problem, or as I said 0th order. And so, this is known to us, and so this solution is known, which means that E n 0 and psi n 0, these are known, and n is the quantum number, whatever it may be. In a given case it could be the angular momentum, in some other case it could be just a linear momentum k, or it could be just energy or quantum number that explicitly expresses energy, like what we have seen in harmonic oscillator or even in hydrogen atom and so on. Okay. So, we want to solve for this E n and psi n. So, these are not known, and what are they? They are the eigen solutions of H, which means the Hamiltonian has these as the eigenvalue and the eigenvectors, and that is not known. So, what we do is the following: we the one that we do not know, write that as the one that we know as this, and plus some unknown coefficients where k is not equal to n, and C n k, which is a function of lambda, and then psi k 0. Okay. So, whenever you see a 0, you understand that 0 corresponds to the unperturbed problem or the 0th order problem. Okay. So, and the C n k is basically the coefficients that are unknown, and C n k is a polynomial in lambda. So, because it is a polynomial in lambda, we can talk about 0th order, first order, second order and so on, and these corrections to the energy and to the wave function would only come from first order, and for some reason the selection rule excludes the first order correction to exist. It may happen at times, then we would resort to the second order calculation. That is now, this will give you the, as I said, the different orders of the perturbation theory. Okay. So, in the 0th order, let us see what happens. That is a known problem, but we still want to get it from the perturbation expansion. So, we have lambda equal to 0. Okay. So, H is simply equal to H 0. So, that tells you that C n k 0, this is equal to 0, and the total psi n has to be equal to psi n 0, which is understandable because you have H equal to H 0. The entire Hamiltonian has eigenstate psi n, which should be nothing but the unperturbed eigenstates of the system. Now, C n k lambda has sort of solution which is C n k 1 plus lambda square C n k 2 plus lambda cube C n k 3 and so on. Okay. And the energy will have a form which is E n 0 plus lambda E n 1 plus lambda square E n 2 plus a lambda cube E n 3 and so on. Okay. This is of course known. Okay. So, if you substitute this into the Schrodinger equation, these all these things that we have learned, then we have a h 0 plus lambda h prime, that is the total Hamiltonian, and this will be on this psi n 0, that is the unperturbed, plus you have these lambda c n k 1. So, this corresponds to the 0th order, lambda n k 1 psi k 0. Well, that 0 I am writing it without a bracket, and so k is not equal to n, and you have k not equal to n again, and you have a lambda square c n k 2, and we have a psi k 0 and so on. Okay. So, this is the left hand side, and the right hand side would be E n 0 corresponding to psi n 0, and plus lambda E n 1 plus lambda square E n 2 and so on, psi n 0 plus lambda c n k 1. So, we are writing the 0 without a bracket in the superscript, but all other orders we are writing it with 1. Anyway, your c n k 0 equal to 0. So, that is not there, but these in the eigenfunction and the eigenvalues will not put a bracket. So, we will simply write it like that. So, that to make this unperturbed problem appear distinct. So, this is psi k 0, and then we have a k not equal to n again, k not equal to n here, lambda square c n k 2, and we have a psi k 0 and so on. Okay. Now, you have terms which are proportional to lambda square and so on both sides, and lambda is a small parameter. So, if this equation has to be satisfied, then we should equate equal powers of lambda on both sides of the equation, and that gives us so match powers of lambda on both sides. So, we have h 0 c n k 1 psi k 0. So, the 0th order is known. So, we are starting from the first order. So, this plus h prime psi n 0 equal to E n 0 and k not equal to n, and we have a c n k 1 and a psi k 0 plus a E n 1 psi n 0 and so on. Okay. So, you see that we have just equated the first power of lambda on both sides. So, if you recognize that h 0 psi k 0, that is a problem that you are familiar with, that is this is known, and psi k 0, then we have this E n 1, which is a first order correction in energy, that acting on psi n 0, this gives you a k not equal to n, and E k 0 minus E n 0 and C n k 1 psi k 0 plus a h prime psi n 0. Now, it is a standard trick to extricate this, or rather to find this E n 1. You have to take an overlap with inner product with psi n 0, or take a conjugate of psi n0, the bra psi n0, and that will give you En1. This is equal to, so this is psi n0. Now, if you take a inner product on the left hand side, the psi n0 will give you 1. So, you are left with En1, that is the first order correction to energy on the left hand side. The first term on right hand side, when you take an overlap with psi n0, it gives you 0. Okay. This gives you 0 because n is not equal to k, and each of these psi n zeros and psi k zeros, this n and k are different labels of the wave function corresponding to the unperturbed problem, and each one of those psi n0 is orthogonal to the psi k0 when n is not equal to k. So, that eliminates the first term on the right hand side, and you are left with this, and even though the calculation seems a little sort of messy, but what you get is that the first order correction to energy is nothing but the expectation value of the perturbation term that you have started with. The perturbation term is here, H0 plus lambda H prime. The lambda H prime is the perturbation term. The lambda is just a dimensionless number, and we are like, when you have a H prime, you know a H prime there, but you cannot solve the problem for H. That is, you can't find the eigenfunctions for H and the eigenvalues for H, but you can treat the problem perturbatively and can arrive at a solution for the first order correction in energy, which is given by the psi n0, H prime psi n0. So, the matrix elements of H prime has to be calculated within the eigenstates of the unperturbed problem, and that is going to give you the first order correction to energy. So, that tells you that at this level, if your perturbation is really weak, then you are doing fine if you just simply take the total En to be equal to En0, which is the unperturbed problem, and the En1 that you find out. So, En1 is here. Okay. En1 can be found out like this. What about the wave function? Let us see the wave function. And so, to calculate the wave function, what we do is that we take an inner product with some with a dummy psi m0, okay. So, what we get is that we get a En0 minus Ek0, that is coming from the first term in inner product of psi m0 and m not equal to n. If m is not equal to n, the left hand side does not give you anything, because if you use this equation and take a overlap with psi m0 with m not equal to n, then this term gives you 0, and this term of course will give you a result, because m can be equal to k and if m may not be equal to k, but it turns out that if m is not equal to k, then this term does not give you anything. And now we get bra psi m0 and H prime psi n0, which means the matrix elements of H prime will have to be calculated between two different orthogonal eigenstates of H, and that is what we do there, and we get this result as En0 minus Ek0, and we have a Cnk1 delta Km, and that is equal to psi m0 H prime psi n0, and this is precisely what you wanted, the Cnk1, but now this will click only when k is equal to m. So, we have a Cnm1, this is equal to psi m0 H prime psi n0 and divided by n0 minus m0. Okay. So, this is the correction to the first eigenfunction. So, what it means is that you have a psi n which is equal to a psi n 0 and plus a C n m 1, and then of course, you have these the one that we have written down here is this psi k 0, or so C n m and a psi m 0 and so on. Okay. So, of course, we have to sum over this m, where m can be any of these indices. Let us see what happens in second order, because as you go higher up in the order, it becomes more and more complicated. Now, you could ask me this question: if this perturbation is weak enough, do we really need to go into the second order? Yes, you don't, you are absolutely correct, but then for some reason you may have the first order correction to the energy to be equal to 0, in which case you have to go to second order. It is an obligation, because otherwise you do not get any correction in the energy due to the perturbation. So, that is an important thing. So, the second order and so this is H 0, and then we have k not equal to n, and we have a C n k 2, and we have a psi k 0 plus H prime, and then we have k not equal to n, and we have C n k 1 psi k 0 equal to E n 0, and then k not equal to n, and you have C n. So, we have this. So, yes, that is correct. So, C n k 2, and we have a psi k 0, and so we are taking up to lambda square. So, only matching terms on left and right up to lambda square, and so this E n 0, and then you have a E n 1, then k not equal to n. E n 1 is of course known, C n k 1 psi k 0, that is known as well, and E n 2 psi n 0. Okay. So, we want to find E n 2 and C n k 2. Okay. So, again in order to do that, you have to take an overlap with psi n 0. So, this is psi n 0. So, take an overlap and so on. So, that makes this E n 2 free, and you have k not equal to n, a little sort of expression that you have to get to, but there is no option. So, we have a psi n 0 and a psi k 0, which again gives you 0, because they are orthogonal, and then we have this plus psi n 0 h prime, and now we put in these values of C n k 1, which are psi k 0 h prime psi n 0 divided by E n 0 minus E k 0. We have already assumed that n is not equal to k. So, the denominator is never going to blow up, and we have a psi k 0. Okay. So, that is the overlap for this term that you see there, the second term on the right, and then you have minus E n 0. So, that is k not equal to n, C n k 2. I mean, these look a little boring, but then they are instructive, because the final result that you arrive at is quite simple. And again, this is equal to 0, because they are orthogonal, and we again have these psi n 0, h prime psi n 0 and so on, and then you have a term which is k not equal to n, and there is a term there, but this is equal to 0 again because h prime. So, psi n is not an eigen state of I mean, so this will give you a term which is I mean not this one. So, this one is okay, but then you have a term which is psi k 0 h prime psi n 0, and then you have a E n 0 minus E k 0, and then you have a psi n 0 and a psi k 0 which is equal to 0 again. Okay. So, you are left with very little number of terms for the second order correction in energy. So, E n 2 is simply equal to a k not equal to n, and we have a psi n 0 h prime psi k 0 and psi k 0 h prime psi n 0, and this is divided by E n 0 minus E k 0, and that is equal to mod square of, so k not equal to n, and we have these psi n 0 h prime psi k 0 and a mod square of that divided by a energy denominator which does not diverge. Okay. So, this is the first order energy correction and so on. I will sort of simply write down this a final result for the wave function which can be easily again determined by the same prescription that you have seen, that is taking an overlap with psi m 0 and all that. So, C n m 2 it's equal to 1 divided by E m 0 minus E n 0. So, this and then there is a sum over k psi m 0 h prime psi k 0 and psi k 0 h prime psi n 0 and minus. So, this divided by another energy denominator which is E k 0 minus E n 0 and minus psi n 0 h prime psi n 0 psi m 0 h prime psi n 0 and E n 0 minus E m 0. Okay. So, most of it we have derived the second order completely up to second order, the energy correction and correction to the wave function, and these will be required for us to proceed further because we will apply it to different cases. And as I said that the first order energy correction being 0, you have no option but to go to the second order to see the correction. It cannot happen that just because the first order is 0, there is no correction that occurs, and in fact we will see that is the case. And this problem is a little more complicated for degenerate perturbation theory, where once again the degeneracy means that you have different eigenstates corresponding to the same energy or the same eigenenergy. And if that happens, you can have this E k 0 and E n 0 to have the same value for a given system, and in that case this formalism it does not work, because it does not make sense that the second order correction to energy or second order correction to the wave function blows up. Then we are not applying the perturbation theory in a controlled fashion. So, a new formalism has to be developed. We thought we will be able to finish that, but nevertheless we will do that in the next class, where we first talk about the degenerate perturbation theory and then hopefully apply it to these hydrogen atom in a weak electric field, which is called as a Stark effect. So, we will stop here with this. We have started with the proximate methods or talking about the perturbation theory, specifically the time independent perturbation theory, and have derived the first order correction to energy, second order correction to energy, first order correction to the wave function, second order correction to the wave function, and they have in general they have complicated terms, but you see everywhere we have the psi k 0, psi m 0, psi n 0, E m 0, E n 0. These are known for a given problem. Suppose we give particle in a box, then these are the different eigenstates of the particle in a box, the ones that we have derived. But so these have to be used in order to calculate the corrections. So we build up our theory from all these quantities that we already know, that is we are aware of these psi m 0, psi n 0, E m 0, E n 0 and all that. So, these are simply the corrections to that in terms of all these eigen solutions of H 0. We will stop here for today and we will carry on with degenerate perturbation theory on the next class. Thank you.